Dear students, in this lecture we go over software reliability testing. According to Wolin, software reliability can be defined as the probability for failure-free operation of a program for a specified time under a specified set of operating conditions. Now, pay attention to the term failure-free. If we interpret this literally, reliability testing would encompass all types of testing. Why? Because all testing by nature aims to ensure that software operates without failure. For instance, regression testing, which ensures that existing functionality remains unaffected, also targets failure-free functionality. But does that mean regression testing is reliability testing? Not quite. We limit reliability testing to specific tests that wouldn't otherwise be conducted during the development process. This is because regression testing, while essential, is a part of functional testing. It ensures the system functions as expected. Reliability testing, on the other hand, focuses on uncovering reliability-related issues that are not found in, for example, functional testing. The primary goal of reliability testing is to evaluate how software behaves under real-world conditions. This is distinctly different from, for example, unit testing, which focuses on individual components in isolation. Reliability testing ensures the software performs reliably when integrated into larger systems and subjected to actual operating environments. Now, why is reliability testing so critical? It's especially vital for mission-critical systems where failures can have severe consequences. Think about industries like aviation, healthcare, and banking, where reliability is non-negotiable. For instance, medical devices must operate without error, and banking systems require consistent uptime to handle transactions securely. The focus of reliability testing is twofold. First, to identify defects that affect the long-term functioning of the software. Second, to minimize downtime or performance issues caused by factors like crashes, slow recovery, or high system loads. Next, we cover different reliability testing approaches. Fault injection testing, also referred to as chaos engineering, is a method of intentionally injecting faults into a running system to observe and evaluate its behavior. The goal here is to uncover weaknesses in the system and understand how it performs under unexpected failures. The types of faults that can be introduced include network problems such as latency, data loss, or outages. It also includes hardware-related issues like disk space exhaustion, CPU overload, or lack of memory. Other common faults are crashes, subsystem unavailability, or general slowness. We can also test for data corruption, database errors, and configuration-related faults that could impact system behavior. Why do we do this? Fault injection helps ensure fault tolerance minimizes the impact or blast radius of any single failure and improves the ability of the system to recover. This testing is critical for systems that need to operate with high reliability. The term chaos engineering was coined by Netflix in 2010. Unlike traditional fault injection testing, chaos engineering is more focused on the whole system level and production environments. It emphasizes reliability as a core pillar of software development excellence, going beyond simply finding bugs. This approach shifts the mindset from we test to find bugs to we engineer systems to survive failure. By adopting chaos engineering practices, we can build resilient systems that thrive even in unpredictable conditions. The lecture playlist contains a video where a Netflix engineer explains their history and current status with chaos engineering. Tools like Chaos Mesh can facilitate fault injection testing by providing a structured way to introduce and manage these faults. Stress testing is about generating extreme levels of stress, load, or activity spikes to evaluate how a system behaves under such conditions. This method is essential for understanding the system's resilience and identifying any breaking points. For example, think about Black Friday sales spikes in e-commerce. These are situations where systems experience an unusually high surge in user requests or data volume. Stress testing prepares systems to handle such scenarios effectively. The focus is on loads higher than normal, which can include network traffic, user requests, or data volumes. What is relevant for testing depends on the specific system, whether the primary concern is user activity, data processing, or a combination of both. During stress testing, we track key metrics like throughput, response times, and error rates. These provide insights into system performance and highlight areas for optimization. The ultimate goal is to identify hardware, software, or infrastructure scaling limitations. By doing this, we can improve scalability and plan for system resilience. Tools like Locust can help simulate these stress scenarios efficiently. Endurance testing, also known as soak testing or longevity testing, evaluates the behavior of a system or service when it is run continuously over extended periods. The key objectives of endurance testing include identifying performance degradation caused by prolonged use, such as increased response times or reduced throughput. Additionally, it involves monitoring resource consumption trends over time, such as CPU usage, memory allocation, and disk utilization, to uncover potential issues. Endurance testing is particularly effective at detecting problems like gradual resource exhaustion, for example, due to memory leaks, that could eventually impact system performance. For example, it helps us understand if and when services need to be restarted to maintain optimal performance. Applications with memory leaks, for instance, may require periodic restarts to avoid severe slowdowns. By identifying these issues early, endurance testing helps ensure that systems can sustain their reliability over time. This type of testing is much rarer than stress or fault injection testing, as lessons learned from endurance testing are often collected from production operation. Let's discuss performance and load testing and its relationship with reliability testing, as they are closely related. Performance testing can be considered part of reliability testing in certain contexts. For example, when dealing with extreme workloads, such as in stress testing, performance testing directly contributes to understanding the reliability of the system. Similarly, when evaluating long-duration runs, as in endurance testing, performance testing helps determine if the system remains stable over extended periods. However, performance testing is not part of reliability testing when it focuses on optimizing the system for normal workloads. In this case, the goal is typically to enhance resource utilization and efficiency rather than assess reliability. The diagram below provides a broader perspective on software product quality. It illustrates the relationship between different attributes such as functional suitability, reliability, performance efficiency, and others. While reliability and performance efficiency are distinct, their roles can overlap depending on the testing context. In conclusion, while performance testing is not strictly reliability testing, it is a vital practice that helps ensure software performs reliably under various conditions. Negative testing is an essential part of ensuring the reliability and robustness of a system. To understand its role, let's first look at its counterpart, positive testing. Positive tests involve providing valid input to verify that the system behaves as expected. For instance, in a login page, when a user enters a valid username and password, they should be granted access and redirected to the application. Negative testing, on the other hand, focuses on invalid input to ensure the system properly handles incorrect or unexpected data. For example, in a login page, if an invalid username or password is entered, the system should return an appropriate error message rather than failing unexpectedly. It's important to include both positive and negative testing in your reliability tests. while positive tests confirm correct behavior. Negative tests ensure the system can handle edge cases and avoid failures under abnormal conditions. Excessive negative tests, such as repeated invalid login attempts, should also be observable in monitoring systems. For example, tracking the ratio of unsuccessful to successful logins can highlight anomalies stemming from attacks, authentication service failures, database issues, or login screen bugs. By covering both types of testing, we can better ensure the system is reliable and secure under various circumstances. Let's summarize our discussion on reliability testing. The concept of reliability itself is clear. It is defined as the probability of failure-free operation of a program for a specified time under a specified set of operating conditions. What can feel elusive, however, is determining which types of testing are considered part of reliability testing. This elusiveness arises because not all testing can be categorized as reliability testing, as they also serve other quality goals. If we were to categorize all testing as reliability testing, the distinction between different test types would become meaningless. For example, fault injection testing, also known as chaos engineering, is clearly part of reliability testing because it simulates faults to evaluate how the system copes. Stress testing, which pushes the system beyond normal operational limits, and endurance testing, which checks for performance degradation over time, are also integral to reliability testing. On the other hand, performance or load testing and negative testing are not strictly part of reliability testing. However, in certain contexts, such as testing extreme workloads or invalid input scenarios, they can be part of reliability testing and provide valuable insights. Reliability testing specifically focuses on ensuring the system performs failure-free under defined conditions, while other types of testing may target performance optimization or functional correctness.